In this video, we're going to be looking at 3D linear equations. We know that in 2 dimensions, a linear equation creates a line. But what about in 3 dimensions? What would be a linear equation? Well, first of all, a linear equation means that the slopes are constant. But what slopes are we talking about? So in a 2-dimensional, we're talking about the change in y over change in x. In 3D, we're talking about the change in z with respect to x and the change in z with respect to y. And both of these slopes need to be constant. And when that happens in 3 dimensions, when both of these slopes are constant, what we get, no longer a line because we're in 3 dimensions, a linear equation in 3D gives us a plane. And planes are a very important feature for us to consider in calculus, or in multivariable calculus, rather. Why? Well, in single variable calculus, we used lines all the time. When we were given a curve, we liked to approximate that curve as a line. So we would draw tangent lines. And the reason why we would draw tangent lines is because it's much easier for us to consider linear relationships than nonlinear. So we could zoom in on an area, and when we zoomed in on any curve, it could be approximated as a line. Similarly, if we zoom in on a 3-dimensional curve, so for example, if we have the function x squared plus y squared, and we graph this, we have this 3-dimensional shape. But if I were to zoom in on it, so instead of from -4 to 4, I looked from -4 to -3.9 in the x and also in the y. So now I'm looking at a much smaller window. What I expect to see is that as we zoom in on this 3-dimensional shape, we should get a plane. And in fact, we do. So the idea is we want to be able to understand, in this section, we want to learn everything about planes, because later on we're going to use planes to approximate curves. But now we're just getting the building blocks for that. And the key things with planes that I mentioned before is that the slopes need to be constant. So the idea is if you were to fix y, keep y constant, and just change x, the z value should change by a constant amount. Similarly, if you fixed our x values and just changed your y, your z value should change by a constant amount. Well, let's think about let's make some motion on getting an equation for a plane. We know that an equation for a linear equation is y equals mx plus b. And so it's a very similar parallel that we can draw. For a plane, you're going to get z equals mx, but there's also y's in here, so ny plus c, where m is the change in z with respect to x, n is the change in z with respect to y, and c is our z-intercept. So once we understand this very simple parallel from 2-dimensional to 3-dimensional, it's pretty easy to do this problem. So we get z equals 2x minus y plus 5. And if we want to see what that looks like, let's go to our computer graphing aid. And we get 2 times x minus y plus 5. We graph it. And let's inspect some of the features of this. So first of all, we notice that our z starts off at a positive value. So this is my z-intercept of 5. If I just look at my x values, so here's my z equals 5, and I've got a positive 2 slope in the x-axis with when I relate x and z. So an increase in x has a positive increase in z. If I keep x fixed and I just look at my y value, so if here's my z-intercept, and notice that I've got a negative slope in the y-axis. This is positive y. So as my y is increasing, my z is going down, and that is because of my negative slope there. Okay, so let's have you try one of these problems. Here it is. Take a second, pause the video, and see if you can get an answer for this. All right, so we're just using the equation z equals mx plus ny plus c, where m is 5, n -2, and c is 3. So here's my equation for z, and this creates a plane that has a z-intercept of 3. In the y direction, there's a negative slope, and in the x direction, a positive slope. So let's add one other equation that we can use. We've been using the slope-intercept. But another equation that we want to be comfortable using is the point-slope form. And these are the same terminologies that we've been using since Algebra 1. And point-slope, we're given our slopes in the x and y direction, and then we're given some point. So as an example, let's say that we know that the slope in the x direction is 2, and in the y direction it's 1, and we contain some point 1, 2, 5. What would be my equation? Well, you'd say z equals my z naught value, although I usually like to put that last. So I'm going to say m, my slope in the x direction, x minus my x value, 1, plus 1, slope in my y direction, y minus my y value, which is 2, plus my c value, 5. And here is an equation for a plane written in point-slope form. So try this one. Pause the video, see if you can get an answer to this, and then unpause it, and we'll move on. Okay, so we've got a point. We've got our slopes. So we get z equals 2x minus 1 minus y minus 2 plus 3. Pretty simple stuff that we're doing. This isn't calculus yet. This is just three-dimensional geometry, but the idea is we're trying to build a basis and understanding of planes so that later on, when we start really doing the calculus piece, we'll know enough about planes so that we can approximate curves as planes. Okay, now getting a little bit more challenging. Let's say we're given 3 points and we want to find an equation of the plane passing through these points. So what we need to do, we have 3 points. We only need 1, but for our point-slope form, but we need to get our slopes, dz dx, or delta z delta x and delta z delta y. So the idea is we're going to look for a place where only the x's are changing and only the y's are changing. So if we look at the first 2 points, for example, notice that my x value stays fixed. When my x value stays fixed, I decrease my y value. And that decrease in my y value from 0 to -1 results in an increase of my z value from 1 to 3. So the slope, the change in z over change in y is -2. Okay, now we need to find a point where my y value doesn't change so that I can see how z changes with x. So if I look at the first and third point here, I notice that when my x value goes from 1 to 3, so it increases by 2, my z value goes from 1 to -1, so it decreases by 2. So this has a slope of -1. So now that I have my slopes, let's use the first point, and we can get an equation for z. We get z equals -1 x minus 1 minus 2 y minus 0, and then plus 1. All right, so we're going to do one more example, and then we'll stop this video and then take a little break, and then you'll go on to the next video. So in this, we're looking at linear relationships in a table. And the idea, I'm gonna move just ahead. A linear function can be recognized from its table if it has the following features. Each row and each column needs to be linear, which means that we're having a constant ratio of change. And all rows must have the same slope, and all columns must have the same slope. They don't the rows and the columns don't have to have the same slope, but every row must have the exact same slope, and every column must have the same slope. But the slope of the rows does not necessarily, it could, but it doesn't necessarily need to equal the slope of the columns. So going back to this problem, what we need to inspect is, as we fix the column, so as we go down, are all of these slopes the same? And if we do some subtraction, so for example, if we get out our calculator and we were to subtract, so I'm subtracting this cell from the one before it, or I could choose any 2 points in a column, subsequent points. So this one, 134. What I expect to see is a constant change. And I do in fact see that of 15,800. So there's a change of 15,800. That's the change in my my revenue when I change my distance tickets by 200. So this slope, I have it down here. This slope ends up being a slope of 79, which means that if I increase my distance tickets by 1, my revenue is going to increase by 79. Similarly, let's think about fixing the distance tickets and only looking at the rows. So the change as I increase my full price tickets, I should see a constant change in the revenue in those rows. And I do. So let's just if I chose those 2 points, if I had 127 200 minus 111 400, doing some basic math here. Whoops, made a small little mistake there, because we should be looking at, sorry, we're looking at the rows right now, not the columns. So it's 27,200 minus 103 times 300. And when I take this difference, you get 23,900. That's the change in my revenue given a change in my full price tickets of 100. So that slope is 239. So if I wanted to get an equation, and if I took the difference in every single, from one row, from one entry to the next, all of these changes are going to be the same change, 239. So if I wanted to get an equation for my revenue as a function of both full price tickets and distance tickets, I could say that my revenue equals, well, let's just choose some point. Let's choose this first point. So my revenue equals the change in revenue as my full price tickets change, so 239 and then full price ticket minus 100 plus this slope, the change in revenue as distance tickets change, so 79, and then D minus this D value, plus my Z value, or my revenue value, 39,700. So this will give me an equation for revenue as a function of full price tickets and distance tickets. So I'm going to stop the video here, and we'll have 2 more videos to watch. Again, the idea of this lesson is getting familiarity with linear functions in 3D.